So we're going back to an older topic today. I'm looking at rates of change. I can't remember who did well and who didn't on the midterm, but this is one person's weak area and then one person's strong area. So we'll
Okay,
see how we
let's
do.
see.
Um, so we are deriving function and solving in terms of variable and then integrating and interpreting rates of change. So I'm going to start out with kind of an older one. I've got this camera at ground level that's filming the liftoff of a space shuttle that's rising vertically according to this position function. S equals 50t. Rest is feet, t is seconds. The camera is 2,000 feet from the launch pad. I want to find the rate of change, the angle of elevation of the camera, 10 seconds after launch. What do I have to do first?
Find an equation.
Okay, find an equation. So what equation should I use? Is there anything that
Um,
relates what we know to what we don't know?
and what's the position equation S equals 50t?
So that's going to tell us this part. So how high the space shuttle is. And it's going to change based on what the time is in seconds after launch. Okay, also
Could
mark
we
this
do
wrong.
a
It's 2,000 feet.
sine function, like sine?
Okay, I could set up a sine function. The problem is we don't know what our hypotenuse is.
Okay, so we just, for the hypotenuse, we do x squared plus c
Okay,
y squared
I could do
plus c squared.
Pythagorean's theorem. So that would give me my hypotenuse in terms of time again. But we can do this without having to solve for the hypotenuse. So, what other trig
So
function could I
can we
use?
derive? Okay.
Right now I know an opposite side and an adjacent side.
The tangent?
Tangent, perfect. Okay, so this is the tangent of our angle equals 50t over 2,000.
Mm-hmm.
Okay. And then if I wanted to solve for the angle right now, I could do that with this formula. So 10 seconds after launch, my angle would be the arctangent of 50 times 10 over 2,000, or 1/4.
Mm-hmm.
Okay, then I can also use this equation to get my derivative. So what happens if I derive this equation?
I have a question. Why did you put 500 and not 50?
Because we are 10 seconds after launch, so that would have been 50 times t, which is 50 times 10, or 500.
Okay. I see.
So this is our angle only at that exact second, 10 seconds after launch. Okay, and then I'm going to take this equation and we're going to derive it to figure out what our change in angle over time is. So what happens when I derive this?
The arc of cosecant squared of 1.
Okay, so this would be secant squared of my... Okay, I'm deriving this one. So secant squared of my angle
Oh, this
times what?
50t over 2,000.
Okay, so that's going to be on this side. But before I get to that, I've got chain rule. So if I derive tangent of theta, I'll get secant squared theta times
d theta over dt.
d theta over dt. Perfect. Okay, if I derive 50 over 2000 t, what will happen?
Uh, 50 over 2000.
Perfect. So that's just a constant times my variable. So when I derive it, I'll just get my constant. If you want to think about it this way, I would get dt over dt with chain rule, which would cancel.
Mm-hmm.
Okay. Then we've got our angle here. So if I want to solve for d theta over dt, I'm going to multiply both sides by what?
Pardon again.
If I want to solve for d theta over dt, I want to get this part alone. What do I have to do?
Move those arcs at the secant
Okay, I'm going to move secant squared.
to the other side.
So secant squared is 1 over cosine squared. So when I move it, I'm just going to multiply by cosine squared. So that'll give me d theta over dt is 50 over 2000 times the cosine squared of my angle, which right now is tangent or arctangent of 1/4. Arctangent 1/4. Okay. So then I can plug that in and get an answer. So this is 50 over 2000 is 1 over 40. Times the cosine of arctangent, 1/4 squared, because our cosine was squared. Okay, it gives us about 0.024-ish. Okay, what are my units?
Feet per second
Say one more time, I'm sorry.
squared. Feet per second squared.
Feet per second squared, not feet per second. This is a change in angle over change in time. What would my angle be measured in right now?
Feet over
So
second.
feet's a measure of length, so we can't use that for an angle.
So just feet.
Nope, feet's a measure of length, and we can't use that for an angle, so there's no feet involved in this at all.
So second.
Okay, so I do have seconds on the bottom. So this is something over seconds. What do we measure the angle in terms of, though? So,
Acceleration.
is this degrees or radians?
Degree.
Okay, so this one's actually radians the way we've solved it right now.
Very good.
Because I did not change my calculator, everything in your Calc AB exam is going to end up being in radians if it involves an angle at all.
Okay.
Okay, so your clue for when you're looking for your units is going to be on this side. So if you're looking at your derivatives will actually tell you the units. This is a change in an angle. Angles are measured in radians over change in time, and our time for this one is measured in seconds. Okay, any questions on this one?
No.
Nope, okay. Let's skip. Okay, so I've got people entering in line for an escalator at this rate. As they get on, they exit at a constant rate of 0.7 people per second. There are 20 people in line at the time 0. I want to know how many people entered the line for the escalator um, between 0 and 300 seconds. Okay, so if I've got a rate, what would the units for this rate be, do you think?
People per second.
People per second, okay. Oh, they actually gave it to us. So people per second. So if I'm in people per second right now, that means this is a velocity. How can I get from a velocity to an amount? How can I get from a rate to an amount?
To integrate.
I need to integrate, okay. So I'm going to integrate from what to what?
0 to 300.
Right, from 0 to 300 of RT. TT. Okay, now this is a with calculator questions. This is the first question here. So I'm going to jump into the calculator for this one.
Okay.
And we'll throw in our rate. So our rate is 44x cubed divided by, oh, it's the whole thing cubed. X divided by 100 cubed times 1 minus x over 300 to the 7th power. Okay, how could I integrate that in my calculator? Do you remember?
Yeah, go on math, and then integrate function.
Okay, math 9. Okay, I've got an older calculator, so this is equation, variable, lower bound, upper bound. So this is our equation, variables, y variables, function, y1, variable,
Call x.
lower bound, upper
0
bound.
to 3.
Okay. Now, on your graphing calculator on the actual test, you'll have an easier job than that because you'll get a GUI and you'll just be able to type in all the pieces of this. Okay, so this is, if I integrate 270, what are my units for this right now?
People.
People. Okay. 270 people entered the line for the escalator. From t equals 0 to t equals 300 seconds.
That's a lot.
Okay, so if you're not sure, we can kind of reuse the question. So I'm kind of using this part. They asked how many people, so I'm going to throw my number out, 270 people, and then just copy the rest of this. So enter the line for the escalator during the time interval 0 to 300 would be a perfect answer.
Okay, yeah.
Cool. Okay, I'm going to check. So scoring guides, we've got 1 point for the integral, looks good, and 1 point for answer of 270. Okay. So part B. From 0 to 300, there are always people in line for the escalator. I want to know how many people are actually in line at the time 300.
So we just plug in 300?
Well, I've got people coming into the line, and I've got people exiting the line. So we've got a rate, constant rate, at which people are exiting the line. So that means our rate of change in people is R of t minus what?
The rate per second, 0.7.
Okay, 0.7. So my change in people would be an amount, not a velocity. So what would I have to do to this?
Integrate.
Okay, I'm going to integrate again. From what to what?
Zero to 300.
From 0 to 300 again. Okay. And then we already had some people in line at the time 0. So this is my change in people in line from 0 to 300 seconds. But I also had some people in line at the start. So how many were already in line at the start?
20.
20. Okay, that was good. So I guess we can do this one in the calculator as well, but I'm going to go ahead and this is second entry, puts out everything that I had last time. And second insert makes it so I don't overwrite. So this is my y1, which is RT, minus 0.7. Okay, so that'll give me my change. And then I'm going to close that integral and add 20.
Okay.
Okay, and that gives us 80. What are our units again?
People.
People. Okay, so there are 80 people are in line for the escalator. At time t equals 300. Okay, again, I'm just kind of using the question against itself. How many people, so there are 80 people, are in line at time t equals 300, are in line at time t equals 300, and you should be okay.
Okay.
Okay, and we'll check our answer there too. Okay, same setup it looks like. Considers the rate out, so we did have a negative 0.07, so we're okay there. And our answer of 80. Okay. Part C. What is the first time that there are no people in line for the escalator?
So we have to set RT to 0.
Well, when RT is 0, that means no people are entering the line for the escalator. But that doesn't mean the line is clear yet.
Um,
Okay, so this rate says we have no more people entering line after 300 seconds. And then how many people did we have in line at 300 seconds from the last problem?
270.
Okay, we had 80 in line from the last problem. At
Last
300 total. Okay, I should write these answers here so we can use them later. Okay, so I've got, at the time 300 seconds, there were still 80 people in line. 80 people in line. No one is entering the line anymore, which means the only thing that's changing the number of people in line is the rate at which they are exiting the line.
Oh, okay.
So if I'm exiting at 0.7 people per second, how can I figure out how many seconds it will take to get rid of 80 people?
80
Okay, 80.
minus the change of rate.
Okay, 80 minus my rate of change. Okay, so this is right now people minus people per second.
Yes.
So if I want to make this people, so people minus people equals 0, what would I have to multiply this 0.7 by?
By the integral of RT.
I'm sorry, say one more time.
By the integral of RT.
The integral of RT. My integral of RT minus our rate already gave us 80. So this is how many people there were at time 300.
Mm.
This is people at t equals 300. Okay, and this is the rate at which they're leaving. People over time leaving. I need this equation to be only in terms of people, so what do I have to multiply this people over time by in order to get people?
Times time.
Times time. Okay, then I can solve for t. That will give us the time after 300. After 300. Where the number of people will reach 0. Okay, are you okay on the setup?
Okay. Yeah.
Okay, cool. So then we can solve for t. This will be 80 equals 0.7 t. So that's 7 over 10, so this will be 800 over 7 will be t. Now this is again the time after 300. Since I started at 300 with my 80. So I will need to add 300 to this to get the actual time. So I could say t equals 300 plus 800 over 7, which is 414.3. seconds. Okay, any questions on what we did there?
No.
Okay, we'll check. Okay, based on part B, there were 80 people here at time 300. So then, okay, we got the same answer and only 1 point per answer, but okay, we look good. Last one for part D. I want to know what time is the number of people in line at a minimum. And to the nearest whole number, find the number of people in line at that time and justify my answer. Okay, so if I want to minimize people, what would I normally do?
Derive.
Okay, derive. So my derivative is RT minus 0.7 is my change in people. Then what? So once you've derived, what do you do?
Set it to equal and then find where the slope is 0.
Okay, I'm going to set it equal to 0. Since this is already my derivative, this is slope. So that means whenever r of t is equal to 0.7, I will be at a critical point. Okay, so I'm going to check for that really quick. So here I've got RFT already in the calculator. I'm going to graph another line for 0.7. And I'm looking for any times between 0 and 300. So I'm going to set my window from 10 to 310 maybe, so we've got enough space. And that should be good. Okay, so there's our RFT and our 0.7. That's a little bit hard to see, so I'm going to zoom in a bit. 1, 2, 3, 4. Okay, so everything looks to be happening between 0 and 4-ish. I'll do that again. Okay, here's our RFT one more time. So that's the rate at which people are entering. And then that's our 0.7. So I just need to calculate these intersects. Okay, first curve, second curve, guess. Okay, my second intersect is 166.574. So I'm going to store really quick. X store alpha B, because that's the second one. Okay, T was 166.57. Nope. Okay, or if I calculate that first intersect instead. First curve, second curve, guess I'm going to say at x equals 10. So that's somewhere around here-ish. Okay, there's our first intersect at 33.01. Second quit, x store alpha A. Okay, so anytime I need that time, I can just type in A. It is 33.013. Okay, so I've got 2 times now. Now, it's also possible for my number of people in line to be at a minimum at a start point or end point. So that means we really have 4 times to test. And then I'll need to know the number of people at that time. So my number of people would be the integral of r of t minus 0.7 dt plus our starting amount of 20 people. Okay, so my starting time was 0. Then I've got time A, time B, and our final time. Because we're only going from 0 to 300, that's it. Okay, so I've got time A and time B. Okay, so I'm going to integrate these really quick and add 20. If I integrate from 0 to 0, there would be no change, so my starting number was at 20. I've already integrated at 300, so we know that number was 80. So I just need A and B.
Yes.
Okay, so this will be... See if I can get back to my integrals so we don't have to retype. There we go. Okay, so my rate minus 0.7 from 0 until, instead of 300, what should be here? So, A, perfect. Okay, so that's 3 people about. That's pretty low. Then we'll do the same thing, stopping at where?
B.
At B. Okay. 158 people.
Okay.
Okay, so taking a look at this, Um, where is t at a minimum?
At point A.
Okay, at the 3.8. So at time t equals a, we are at a minimum. Okay, so at t equals 33.013, there is a minimum number of 3 or 4 people in line. As the change in people is 0, and the number of people is smaller than the start and end point. Okay, we'll see how they worded that next time, but okay, so we've got considers RT minus 0.7 equals 0. Okay, we did that. Identifies T equals 33.013. Okay, we did that. Our answers, there are 4 people online. Okay, we got that. And our justification. They just said it's at a minimum. Okay, I think we'd get that because we did say it was at a minimum.
Okay.
Wasn't sure how much they were looking for there. Any questions on these rates of change?
No, it's good.
Okay, so on Skype, I've sent you a number of other sample free response questions with the answers, and then 2 free response questions that I want you guys to try. So you need to complete those 2 free response questions before Thursday at 9 a.m. So that's for our next class.
Okay.
Okay, thank you very
Okay.
much.
Okay, thank you.